Okay, great. So we continue with Ibrahim, who will tell us about a local quasimorphism property for linked spectral invariants. Go ahead.
So thank you very much for the invitation. So today we'll talk to you about the local quasimorphism property for linked spectral invariants. And this is a joint work with Cheuk Yu Mak. So first of all, let me start with some context and motivations. So for me, a Lagrangian link will be a union of circles inside a surface. I will give more details later about the condition I impose on such a link. But so under some conditions on the link, we can define spectral invariant CL from the universal cover of Hamiltonian diffeomorphisms of a surface to R. Well, here the universal cover is not really important because when sigma is not S2, it's just the same as ham of sigma. So they were introduced by Cristofaro-Gardiner, Humilière, Mak, Seyfaddini, and Smith. This was built on earlier works of Mak and Smith and Petrovich-Sheluchin, where they studied some Lagrangian configurations in S2 times S2. And they were well, they come from computing Lagrangian spectral invariants of a product torus coming from taking the product of each component of the link inside the symmetric power of the surface. And they were first used by CGH-MSS to prove the simplicity conjecture on any surface, possibly with boundary. So let me explain what this conjecture is, what this theorem is. So we denote by ham bar of sigma the group of Hamiltonian homeomorphisms that are compactly supported inside the interior of the surface sigma. And here by Hamiltonian homeomorphism, I mean a C0 limit of Hamiltonian diffeomorphisms. So they showed using those linked spectral invariants that ham bar of sigma is not simple. And in fact, they showed that the subgroup called hameo of sigma is a proper normal subgroup. So for those of you who don't know what hameo is, I will not give a fully detailed definition, but you can think of it as Hamiltonian homeomorphisms that are generated by some continuous Hamiltonian function. And moreover, they show that the linked spectral invariants are quasimorphisms on ham tilde of S2, meaning that the difference between the spectral invariant of phi and psi and CL of phi plus CL of psi is bounded for every two element phi and psi in ham tilde of S2. So you can think of this as meaning that CL is an honest group homomorphism up to some bounded error. And with this quasimorphism property, they managed to show that the Calabi homomorphism extends to a group homomorphism from ham bar of the disk to the real line. So here I recall the definition of the Calabi homomorphism. It's given by the integral of h over the surface sum over time for any Hamiltonian h generating phi that is compactly supported in the interior of the surface. Yeah, and so this Calabi homomorphism is only well defined on surfaces with non-empty boundary. And they also show with the quasimorphism property that this subgroup hameo of S2 is itself not simple. This all relies on the quasimorphism property, but however, we do not expect the spectral invariants on higher genus surfaces to be quasimorphisms. I will give more explanation later as to why. And so therefore, their results only hold for the disk and the sphere and not for higher genus surfaces. So our main results with Cheuk Yu Mak are the following. We consider a topological disk inside the surface sigma, and we denote by ham sub d of sigma the sets of Hamiltonian diffeomorphisms of sigma that are supported in D. And then we generalize their results. So to higher genus surfaces, no, sorry, we prove that under some hypothesis on the link, the restriction of the link spectral invariant to Ham sub D of sigma will be a quasimorphism. And from this, we can generalize CGHMSS results, as we show that for any surface sigma with boundary, the Calabi homomorphism extends to a group homomorphism from Ham bar to R. And for sigma closed, Hameo of sigma is not simple. So maybe I can give you here some explanation as to why this result can be interesting. So first of all, the fact that Calabi extends to a group homomorphism of Ham bar to R means that one can take its kernel, and this gives us a new proper normal subgroup of Ham bar. So this gives us a new proof of the non-simplicity of Ham bar of sigma. And the fact that Hameo of sigma is not simple, tells us more about the algebraic structure of Ham bar of sigma. And also the local quasimorphism property might have independent interest, because the CLs are Hofer-Lipschitz maps. And so having Hofer-Lipschitz quasimorphism might be really useful to study the large-scale Hofer geometry of some sets. Okay, so now in the rest of the talk, I will explain how we prove the local quasimorphism property. But first of all, I will give more details about the definition of link spectral invariants as done by CGHMSS. So what we call a monotone Lagrangian link on a closed surface is a disjoint union of circles, L equal L1 union K, such that every connected component of the complement of the link is planar and have the same area. So as you see in this picture, we can have nested circles. This is not a problem. They can be contractible or not. But here, since we have genus, we need at least as many non-contractible components in our link as we have genus. Otherwise, the planarity condition would fail. Okay, so now we will take a Hamiltonian on our surface sigma, and we want to associate to it a Floer theoretical invariant CL of H. So a naive idea would be to take the product of the component of the link. This gives us a torus inside sigma to the K. So it's a Lagrangian torus. But as you can see, if I have here a small contractible circle, it is displaceable inside the surface. So the product torus will be displaceable inside sigma to the K. And so its Floer homology will vanish, and there is no way to define spectral invariance with that. So what CGHMSS do is that they take the quotient by the permutation group, and they obtain a monotone Lagrangian sim L inside the symmetric product of the surface sim K of sigma. Well, as it is, like the symplectic form sigma to the K descends to a form on sim K, but it is not smooth. And so one needs to smooth it out near the singular locus away from sim L. And this can be done following work of Perutz. And yeah, the monotonicity here is a consequence of the area conditions we have on the link. So now that we have our links and our Lagrangian in the symmetric product, we will compute its Floer homology. So we define a Hamiltonian on sim K of sigma the following way. So here, yeah, so at a point x1, xk, so this is a point in the symmetric product. So it's basically k points on our surface, but it's unordered. So I write it as a set. So sim k of h is defined as the sum of h at each coordinate, and we will denote by phi its time one map. Then we choose a point x on the Lagrangian sim L, and we denote by gamma its trajectory under the flow of sim k of h. This will serve as a reference path to define the cappings and the action. And the Floer complex will be generated by equivalence classes of capped intersection points between sim L and its image, and the differential will count J holomorphic strips with Lagrangian boundary conditions. So I drew a picture here. I have my point that I choose on the Lagrangian X. So here is sim L, its image phi of sim L. I have this point X and its trajectory gamma. And so the generators are intersection points Y together with a capping from gamma to Y that you can see here in green. And the differential count strips from capped intersection point Y to Z, for instance, here. Okay, so then they show that the Floer homology of sim L does not vanish. It's actually isomorphic to the Morse homology of sim L tensored with Novikov coefficients. And yeah, sim L is just a product of circles, so it's a k-dimensional torus. And this is shown by analyzing the disk potential for this Lagrangian. So we will be able to define spectral invariance, but for this we need a filtration on the Floer complex. So we define an action functional in this way, given a generator Y. So Y is an intersection point and W a capping. Its action is given by minus the symplectic area of the capping, plus some term here that, as you can see, does not depend on the generator. So it's just a constant we add. Here, X is the point we chose on our Lagrangian. And so this term is just added to make the action functional more natural. As if we change the point we choose X, then the capping will also change, but the difference would stay the same. So the action does not depend on the choice of reference point X. And so now that we have the action functional, we can define the spectral invariant CL of H as 1 over K, so this is just a renormalization term, times the minimal action of a representative of the fundamental class. Then one can show that this quantity is homotopy invariant, and so CL descends to a map from ham tilde of sigma to R. And when sigma is the sphere, the two sphere, CL is a quasimorphism. And this is because sim K of S2 with the Perutz type symplectic form is actually symplectomorphic to CPK with the Fubini study form. And we know that the quantum cohomology of CPK is semi-simple. And there is a result by Yentov and Poltrovich that show that when the quantum cohomology is semi-simple, the spectral invariants will be quasimorphisms. So this is why the link spectral invariants are quasimorphisms on S2. However, when the surface is not the sphere, the quantum cohomology of sim K of sigma is not semi-simple. It was actually computed by Bertram and Thaddeus. And so we cannot deduce from this that the spectral invariants are quasimorphisms. So now I will move on to the proof of our result that I recall here. So yes, as I stated before, I need some additional hypothesis on the link L for our theorem. So I have a disk inside my surface sigma, and I will assume that the link L is monotone and that it has exactly G non-contractible components, alpha 1 to alpha G. And moreover, that all those non-contractible components are away from the disk D. Then we show that the restriction of the link spectral invariant CL to ham sub D of sigma is a quasimorphism. So to show this, we decompose the surface sigma as a connected sum of a surface sigma prime with a torus containing this component alpha G. And we will write, we will define L prime as L from which we removed alpha G. So now it's a link in this smaller genus surface sigma prime. And it has K minus 1 components. And we show a Kunev formula for this decomposition in Floer homology. So if I take a Hamiltonian supported in the disk T, I take a small perturbation to make everything transverse. Then we have a natural filtered chain isomorphism between the Floer complex for sim L inside the connected sum, so sigma, and the tensor product of the Floer complex for sim L prime, which lives in sigma prime, and the Floer complex for alpha G inside the torus T. And so when I say that it is natural, it means that it commutes with continuation maps supported in the disk T. And in particular, from this filtered chain isomorphism, we get the equality of the spectral invariants up to renormalization. And so if we view our surface sigma as a connected sum of a sphere containing the disk T and all the contractible components together with G different tori, we can apply this result G times to get that the spectral invariant in the surface sigma will coincide with the spectral invariant computed inside the sphere, for which we know that it is a quasimorphism. So the local quasimorphism property is a consequence of this theorem here. So now I will explain how we prove this QNet formula. So first of all, we show that we have a filtered isomorphism of lambda modules. We construct a map in this way. So if we take a generator of this complex here, it consists of a capped intersection point. So an intersection point in sim k minus 1 of sigma prime is just k minus 1 points that I denote by x. And a generator here is an intersection point between alpha G and its image. So it's a point C. And then I associate to that the union of the k minus 1 points with this new point. So this gives me k points on sigma. So it's a point in sim k of sigma. And well, we also need to take care of the cappings, but this is not too difficult. And one can check that the capping that we associate have the same area. So this is a filtered isomorphism. Then the second step is to show that this is a chain map so that it commutes with the differential. And so to do this, we identify moduli spaces. So as you can see, there are two components in the differential on the tensor product. So we first take care of this one. So if we have a strip contributing to the differential of C, so it's a strip in some moduli space of strips from C to some other point C prime, we want to associate to it a strip starting at X union C, going to X union C prime. This is not too hard because if we have a strip from C to C prime inside the torus, it will never intersect the connected sum region. So this gives us a well-defined strip inside the connected sum, and we just take the product with the constant strip at X. So this gives us this identification. And the second part is a bit harder. So we need to consider strips from some point X to Y inside sim k minus 1 of sigma prime. And we want to associate to it a strip from X union C to Y union C. But now strips from X to Y can pass through the connected sum region, and so it becomes harder. So to do this, we follow some ideas of Osvas and Szabo. So if we have so we have here our connected sum. And if we have a strip that passes through the connected sum region, we take its product with the constant strip at C. What we will do is we remove a small neighborhood of where it passes through this region, and we will glue a sphere in sim2 of E at this point to give us a strip. But now this strip is not holomorphic. If we like build this map naively, but we can show that if we take an almost complex structure that stretches this neck long enough, this map will be close to a unique J holomorphic strip. And so this gives us a construction of a map in here. And finally, to show that this construction, so this map from MXY to MX union C, Y union C is surjective, we use some Gromov compactness argument. Okay. Thank you very much for your attention.
Thank you. Any questions?
I have a question. So, in principle, one gets quasimorphisms under weaker assumption than semi-simplicity of quantum cohomology. One needs the field factor. Did you check it?
I didn't check, but I believe, well, we have some example. For instance, if you take just a torus and you take only one Lagrangian, we know in this case that the spectral invariant is not a quasimorphism.
Yes, that's true, of course.
Yes, and so we expect that if you take more components, it will not it will not help with that.
And higher genus will not help, you say?
I think so, yes.
Okay, and another question. So, how defect of your quasimorphism depends on the chosen disk?
In the end, we show that it coincides with the quasimorphism on the sphere, for which the defect depends only on the number of components. So it does not depend on the disk.
On area, it doesn't depend.
No.
Interesting. Thank you. Thank you.
Okay, great. Thank you, Ibrahim, again.